So we are basically continuing with more consequences of Cauchy's formula. Right? Cauchy's formula is the great tool. We have it. We're gonna milk it for all it's worth. So what we're going to go for today is something called the maximum modulus principle. Okay, we'll see the maximum modulus principle for the case of analytic functions, and we'll also see it for the case of harmonic functions. And then we'll talk about something called the Dirichlet problem, and how we can solve the Dirichlet problem in a simple, in the case of a unit disk. Okay. Okay. So maximum modulus principle roughly says that if you have an open connected region, let's say that it's bounded. If you have an open connected bounded region, then if you have a function that's analytic on that region, then it cannot attain a maximum within that region. If you look at the function and it's continuous on the closure, then the maximum has to occur on the boundary. Okay, so the maximum cannot occur within the region itself. Okay, so first thing we need to get is something called the mean value property of analytic functions, and this is an immediate consequence of, so for analytic functions, this is an immediate consequence of Cauchy's formula. So we're just going to derive it here. So let C sub rho be a circle, be the circle z minus z naught equals rho. Okay, so you have some point rho, you have a radius, there's some point z naught, there's a radius rho, and you're looking at the circle, the positively oriented circle around that point of radius rho. Okay, and say that f is analytic on this circle and inside of it. Well, by Cauchy's formula, tells you that that f of z naught is 1 over 2 pi I, the integral over c sub rho, f of z minus z naught dz. Right? That's just Cauchy's formula. Okay, and then if you evaluate that, what you get is 1 over 2 pi. I do need to go up here. 1 over 2 pi. 2 pi I. Integral from 0 to 2 pi of f of z naught plus rho e I theta over rho e I theta, I rho e to the I theta to theta. Right. Should I let you set that up? Maybe I should have just let you do it. Anyway, it's up on the board. Too late. But you see what we're doing, right? You take your gamma to be z naught plus rho e I theta, as theta ranges from 0 to 2 pi. Right? This is just f of gamma of naught, right? Gamma naught minus z. That's this, and then there's gamma prime. Right? So we're just evaluating the integral. Okay. And you see what happens, right? Things cancel out. These things cancel out. These things cancel out. Right? And what you get is this. And this is this right here is what we call the mean value formula, the mean value property. So you see what it says, right? Whenever you have a function, you have a function and you have a disk. The function is analytic on that disk. Then on and within that disk, then the value at the center equals this average of the values on the boundary. Right? The value at the center equals this average of the values on the boundary. The mean value property of analytic functions. Any questions? Yeah, no? Everyone all right? Okay. Okay. So that turns out to be pretty. Binding condition. It gives us something that we're going to call the local maximum modulus principle. Okay. Say f is analytic on some epsilon neighborhood and epsilon is not. And say that the value of f at the center, the size of f at the center is maximal. Okay. In that case, then f must be constant. Then f must be constant. Okay. Has anyone taken a look at this in the book? Does anyone want to venture the explanation of this? Of course, we're going to use the mean value. We're going to use the mean value property, right? Anyone take a look at it? No. Take a look. Yes. I should make you read the books. Read the book. But in fact, I'm going to give a different proof from the book anyway. So here's one way to prove it. I like the proof in the book. It's nice. It's actually maybe how probably I think most people would go about trying to do it by contradiction. But I'll give you a sort of clean, slick proof. Okay, so fix any rho that's smaller than epsilon. So rho is some positive number smaller than epsilon. We have the mean value property, right? So the mean value property says that f of z naught equals 1 over 2 pi, 0 to 2 pi, f of z naught plus rho equal to theta. Okay. So in particular, if we take the size of this, we know that it's controlled by the average of the moduli of the values on the circle. Right? right? But we also know that, what else do we know? We know that all of these values are they're f less than f of z naught, right? So what? So we get the integral of f of the modulus of f of z naught from 0 to 2 pi divided by 2 pi. And so we get, again, we get this. Right? Well, what is that force? Does anyone see? Do you see how it finishes up? Right? How does it finish up?
They're all equal.
They're all equal, right? All of these values have to be f of the modulus of f of z naught, right? And this was an arbitrary. Right? We took this. Here was epsilon. We took any row, and what we're saying is that at any point on the circle, at any point on any circle, the values of the modulus of f there equals the modulus of f in the middle, right? And so we get it for every point within the circle. Okay. To make it maybe even more clear, we say, well, take that and then subtract everything from f of z naught, right? Then you see that 0 is less than or equal to f of z naught minus right. You just subtract everything from f of z naught, right? The number f of z naught. Right. And so you see, well, that this integral, it's an integral of something positive, right? Because f of z naught was the maximum, so you're integrating something positive, or you're integrating something non-negative, and you get 0, so it must be 0 throughout, right? And so this, right? So we know that f of z naught plus rho e by theta modulus must be equal to this for all theta, and rho was arbitrary, so we get it for every point inside the neighborhood. The proof that they give in the book is like this. It's basically the same proof. You say, well, suppose that at some point this is strictly less than the modulus of this. Right? Well, that will tell you that in some little neighborhood here, this thing is going to be less than that. Okay, and if that happens, you basically set it up that this thing will have to be less than or equal to itself, right? Because you get that this thing is less than or equal to this, but integrating over that circle in which there's one point where the value is lower, you're going to end up with something strictly smaller than f of z naught's modulus, and so you get a number would be, this modulus would be less than or equal to itself. I mean, less than itself, strictly less than itself. So that's maybe a more straightforward way of doing it, but that's okay too. Okay. Yeah, Michael.
So, what is the notation of 3 bars? What is that?
Constantly equal to is a constant. F of z is a constant function.
Yes.
Constantly.
I guess I'm confused. So if you have the moduli that are equal to each other, how does it immediately follow that the function values are necessarily?
It's wrong. If you have an analytic function whose modulus is constant, then if you use the Cauchy-Riemann equations on it, then you can see that the function itself must be constant. In fact, I think I gave you that as homework.
Don't you also know that it's bounded though? So don't you get that from Louisville? Or how do you say?
No, because you don't have an entire function. needs to be an entire function, bounded entire function for that to happen. Okay, so yeah, so it is, so anyway, so the modulus is constant. So modulus is constant, which forces F itself to be constant. Okay, sorry.
Wait, sorry, why is that entire?
It follows, it's, I think I gave this as a homework problem, but it follows from the Cauchy-Riemann equations. I didn't give this, did I?
Yeah,
Yeah,
F is analytic then, and then F is constant.
Yeah. Okay, sorry. Okay. Okay. Well, now that we have the local maximum modulus principle, we can get the global maximum modulus principle. Which is this, B be an open connected set. And let F be analytic on B. If F is non-constant on B, is non-constant on D, then modulus does not attain a max. Okay, so let's see if I can prove this. So I'm going to prove it again. I'm going to prove it in a rather, actually this time a rather different way from in the text. But here we go. Suppose F attains the max at some Z naught. Okay. So we have an open connected set, right? It's, as we know, it's also path connected. Let zeta denote an arbitrary point. Okay. And what we're going to show is that f is forced to be a constant function. Okay. Suppose f modulus of f actually does attain a max. We're going to see that here's Z naught. That's when the max is attained. We're going to see that every point has to have the same value as this point. Okay. So attaining a max forces you to be a constant function. If you're non-constant, you're not going to attain a max. Okay. So let C be a contour from Z naught to zeta within B. You choose the polygon zeta, and you have some contour linking those two guys together. Okay. At this point, we're going to use the path covering lemma that we brought out earlier. Right? So by the path covering lemma, we spent so much time creating it. Let's use it. There exists a row greater than 0. And some sequence, Z0, Z1, Zn, sequence of points along C, such that each disk B row Zi contains the the next time, the zi plus 1. At least up to the last one. So for I belong to C and this one. Okay. So there's this sequence of points, and there's a row so that each row ball around one of these centers contains the guy before and the guy after, right? But in particular, it contains the one after. Okay. Okay. Can anyone see the end from here?
Just apply the local one.
Apply the local one. Yeah, just apply the local by the local maximum modulus principle. We know that since the maximum occurs in the center of this first ball, then the function must be constant on that first ball, right? But that means that at z1, the value is the same as at z0. Well, that means that z1 is also a max, right? And then you say, well, you apply the local maximum modulus principle to the second ball, right? That forces the function on the second ball to be constant, forces the function on the third ball to be constant, blah, blah, blah. And so f of zeta equals f of z0, etc.
I was just going to say, how do you know? So like, in their intersection, then all of it has to be constant in the next one. How do you know there's not something bigger somewhere else in that?
Somewhere else?
Like outside the intersection of the first one and the next one.
Well, so zeta was an arbitrary point, right? Zeta was an arbitrary point. So you say, well, let's choose any other zeta. We know that the value there is going to be the same as the value here.
No, I mean like once you fix the zeta and you apply this argument with these circles. So you had the argument for why the first one's constant. So how do you get from there to the next one must be constant?
Oh, okay. So by the local maximum modulus principle, you know that since f of z0 is bigger than f of z for all z within the neighborhood, we know that f is constant on the first row neighborhood, right? But this row neighborhood contains z1, right?
So you can put a neighborhood around z1.
Right. So f of z1 is equal to f of z0, right? But remember, that means that that f of z1 is the max, right? So f of z1 is the max, is a max over the whole domain, right? And then you just iterate. You just do it again. You do it n times. Get f of z2, blah blah blah. So and you get that f of zeta equals f of z0. So the function is constant. Okay. Any questions? So as a consequence, you can phrase things this way: corollary. F is analytic and non-constant on a bounded, open, connected set D. And if F is continuous on the closure of D, then the modulus contains its max on the boundary. Okay, where the boundary is the closure excluding the open set D. The closure minus the open set. Right? Is that obvious to everybody? Right. You know that we know F attains. I'm sorry. F modulus of F attains a max on D closure, right? Because D closure is a compact set. You have a continuous function on a compact set, right? So you know that there's going to be a max somewhere. Right? But that max, if your function is non-constant, that max can't occur inside D itself. So it must occur on the part of D bar that's not in D, namely the boundary. Right. The max modulus principle, that max is not. So it occurs on the boundary. Is this exciting? I don't know if this is exciting. Maybe it's not that exciting. So there's a consequence in the text. They give this consequence called Schwarz's lemma. I'm going to let you read Schwarz's lemma because to me, you were kind of bored, so I'm going to just try to get into other things. So anyway, read Schwarz's lemma. The proof is pretty straightforward. Okay. So now we're going to switch over to harmonic functions. So remember, harmonic functions are those that satisfy Laplace's equation. Laplacian is going to be 0. And recall that if U is harmonic and there exists a V such that U plus IV is analytic, then we call V a harmonic conjugate of U, a harmonic conjugate. And we will show something that we mentioned before about the existence of harmonic conjugates. So let A be a domain. That's to say an open connected set. And let U be a twice continuously differentiable function. So twice continuously differentiable function on A. then if U is harmonic, then in fact it's the infinity. Okay? It's infinitely differentiable. And further, for each Z naught in A, there exists a ball in which U is the real part of some analytic function. So there, given any point, there's a neighborhood in which a harmonic conjugate exists. In part 2, if A is simply connected, then there exists an analytic F on A such that U is the real part of that analytic function. So if you're simply connected, then you're guaranteed a harmonic conjugate for the whole set. Okay, and you see that the first part is actually a consequence of the second part, right? Because if you're not simply connected, well, any point in this open set is contained in some ball, right? Is contained in some ball, and you say, okay, well, within that ball, the ball is simply connected, so I know that within that ball there's an analytic function, so that my U is the real part of that analytic function, right? But if that's true, you are the real part of this analytic function, which means that you're infinitely differentiable, right? Because the analytic function, by Cauchy's formula, we saw all analytic functions are infinitely differentiable, so you're automatically infinitely differentiable, and in that ball, you're going to be the real part of some analytic function. Okay? So all we need to do is prove part 2, and then part 1 follows immediately. Okay, so the proof is not really exciting. It's more of a calculation. So here it is. Let G be the partial of U with respect to x minus I times the partial of U with respect to y. And let's call that capital U plus I capital V. Claim is that G is analytic. Okay, so so should I let you do it? I'll let you try and do it. Okay. Prove that G is analytic. What do you need to do? So what do you need to do? Cauchy-Riemann equations, right? So you say, okay, let's take the partial of u with respect to x. Partial of capital U with respect to x is the second partial of little u, right? Let's take the partial of v with respect to y, right? And you get negative. You get this. And you're hoping that those things are equal to each other. Why are they equal to each other? Why are this and this equal to each other? Because the function's harmonic. Right? Second part, you show partial of v with respect to y equals negative partial of v with respect to x. So again, you take partial of v with respect to x, negative that, and you get partial v with respect to x, y, right? And so those are equal as long as these things are twice continuously differentiable, right? As long as u is twice continuously differentiable, then by Clairaut's theorem, you're allowed to switch the order of the partials. Right? So this is by Clairaut's theorem, which is what we just said. You know, if you have a function that's twice continuously differentiable, then it's okay to switch the order of the mixed partials are equal to each other. And certainly u and v have continuous partials, continuous first partials by hypothesis. Because we said u is twice continuously differentiable. So G is analytic. Okay. So since A is simply connected, there exists an analytic f on A such that f prime equals G. So there exists simply, if you're analytic on a simply connected set, then you know that there exists an anti-derivative. Write f as u tilde plus iv tilde. Then f prime equaling G tells you that gives you this equality. Right? This is f prime, and this is G. This is G here. Right? So that tells you that du dx equals du tilde dx equals du dx, and du dy du tilde dy equals du dy. So what does that tell you? That tells you that u tilde differs from u by a constant. So that tells you that u is the real part of f minus this constant. So u has a harmonic conjugate. questions? Okay. It's one can also, for harmonic functions, one can also get a mean value property for harmonic functions. Basically, all you need to do is say, you know that U can be completed into an analytic function, and so you have a mean value property for the corresponding analytic function, and then you take the real part of that. And you get the mean value property for the harmonic function. Okay, so it basically follows from this theorem, right? Or the book gives a sort of cooler way of doing it, but I think it makes more sense to think to use the previous thing. Right? You know that U is that U has a harmonic conjugate, and so you just add on the harmonic conjugate, get an analytic function, and then you have a mean value property for that analytic function, and you take the real parts of that, and that gives you the mean value property. So if U is harmonic on an open set containing a closed ball, it's a bar to not, then U at the center is U of Z naught plus I e I theta. So you get a mean value property for this harmonic function, just like you get the mean value property for the analytic functions. Right. And if you go back and you think about what did we need to get the local maximum modulus principle for the analytic functions?
The integral formula?
Just that integral formula, this integral formula, right? And so if you have a harmonic function that attains its maximum at the center of a ball, well, you can play the exact same game, right? And say, well, then the harmonic function must be constant on that ball. So the mean value property, all you needed was the mean value property to get the local maximum modulus principle. Right. So we still have the local maximum modulus principle. Further, what did we need to get the global maximum modulus principle?
Path covering lemma.
Just the path covering lemma and the local one. So as long as you assume that you're in a case where the path covering lemma holds, right? That is, we're in some path connected set, right? As long as we're in some open path connected set, then you know that the global maximum modulus principle also holds. Okay. So this is good. You get all these things that follow pretty easily. Okay, so now we're going to do something exciting, which is the Poisson integral formula. Okay, so let me sort of set this up for you. It's funny, when you plot out the lecture, you think, oh, this is pretty interesting. I think I'll like this, but you never know how people are going to react. So in any case, even if you don't like this, I like what we're about to do. So here's the problem. So let me sort of lay it out for you here. So you have some domain. Okay, you have some domain. And you specify the values on the boundary. Okay. You specify the values on the boundary of that domain. Okay. And your question is, can you find a function that's harmonic on the interior and which attains those boundary values? Okay. This actually corresponds to a physical problem, which is what is the physical problem? Right. If you have an object in a two-dimensional world, okay, but you can do this in 3 dimensions. If you have an object in a two-dimensional world, and you know that you leave it alone for a while, you've here it's reached a steady state, okay, in terms of its heat, okay, and like you've applied you have some heat being applied to it at some point, and it reaches a state of equilibrium. Okay. And you know the values on the boundary. Is it possible to determine the values of the temperature on the interior? Okay, because the interior, such a system at equilibrium actually is a harmonic function. So the question is, if you know the boundary values, can you tell what harmonic function is on the interior? Okay. Can you create a harmonic function on the interior? And the answer is yes. The answer is pretty remarkable. Basically, for any simply connected domain, you can do this. Okay, any simply connected domain. If you have the values on the boundary, then it's possible to create a function on the interior that's harmonic and attains those boundary values. Okay. Now, half of this is something called the Riemann mapping theorem, which we will not do. But the other half is doing it for a disk, okay, solving this problem for a disk. And then the Riemann mapping theorem allows you to go from the disk to any simply connected domain. Okay, so so we're going to have something called the Poisson integral formula, which will be the key to solving the Dirichlet problem on the disk. So here's the theorem. Let f be an analytic function on and within the circle C naught of radius R naught around the origin, say. Okay. If U is the real part of that, then for all R less than or equal to R naught, we have the formula for U at R E I theta. Okay. And that formula will be that we can obtain it as the integral from 0 to 2 pi of R naught squared minus R squared U R naught e to the I phi over R naught squared minus 2 R naught R cosine phi minus theta plus R squared d phi. So let me sort of try to talk about how this solves our problem. Let's see. So we call call, define the Poisson kernel P by P of R naught R P minus theta being this thing that we're integrating against. Okay, this R naught squared minus R squared over R naught squared minus 2 R naught R cosine P minus theta plus R squared. So, we could write this formula as the integral of the Poisson kernel against U. Let me introduce something else. Given two functions, f and g, we define the convolution f convolved with g by f convolved. The convolution at x is the integral of f of x minus y dy dy. Okay. So for example, if I let my g be, say, 1 over the length of an interval times the, say, like the unit, let I be the unit interval from -1/2 to +1/2. Okay. Let I be this interval from -1/2 to +1/2. Okay. What happens? What do you get when you convolve f against g? What do you get when you do that? What do you get when you do that? Well, you're going to get the integral, y. I'm sorry. So I probably you don't know what this is. So this is the characteristic function which takes on the value 1 there and is 0 elsewhere. Sorry. Okay. So what's going to happen is that this thing is going to be 1 between -1/2 and 1/2, right? And it's going to be 0 elsewhere. So what are you going to end up with? You're going to end up with the integral of f over the interval, the unit interval centered at x. You see that? You're going to end up with the integral of f over the unit interval centered at x, and then divided by the length of that interval. Okay. Right. And now what happens if I let the length of I shrink? Well, I'm going to, as I convolve against these different guys, so let's say I have these I sub n's, and the length of I sub n is 1 over n. Okay. As I convolve against the g sub n's, I'm taking averages of my function f as the interval around x as the interval shrinks to 0, right? So that will tend to, if the function is continuous, then that's going to tend to the value of the function at x. That's going to recover the function at x. Okay. This is basically what's going to happen here. Okay. This thing here is you can think of it as some sort of averaging. It's not something like this, right? It's not a bunch of things like this, but rather it's a continuous version of it, right? It's something like this. Let's pause it. Right, and then they start going higher and higher as your R gets closer to R naught. Okay, so anyway, just to give you some sense of what's going on here, this is basically an averaging of your function, which as R gets closer to R naught, right? And remember what these terms mean. R naught is the boundary of the disk, right? As R, the point where you're evaluating, gets closer to R naught, this convolution is going to approach your original value. Okay. Your convolution is going to approach your original value, and it's going to thus tend back to the values that you specified on the boundary. Okay. So, right, what this thing here is the values that you specified on the boundary. Right. This is u at R naught theta naught. Right. This is u at R naught theta naught. Right. It's the I'm sorry, u at R naught phi, where phi is some whatever angle out here, and you're looking at these are the boundary values. Okay. And so you're creating something. You're creating this function. You start off with the boundary values, and then you convolve it with the Poisson kernel. And what you do, because of certain properties, because of a certain niceness of the Poisson kernel, is as R tends to R naught, well, you're going to recover this function. In other words, as you get closer to the boundary, you recover the boundary values. Further, it's possible to see that this thing is harmonic.